In this video, you will see the vLLM benchmarking results of running the Llama 3.1 405B model on AMD MI300X GPUs. These were the results I got, and in the video you will see how I got these exactly, what the model configuration was, etc. So the first part is deploying the model, and for this benchmark, this is how we have deployed the model. We are using the 405B model weights from Hugging Face, and we're using the AMD published quantized FP8 version of it. We're setting the context length to 120,000, and then we're setting batch tokens and maximum sequences to the max that we think is feasible. We set tensor parallel to 8, so we can use all 8 GPUs, and the model is split across the 8 GPUs. We also set the recommended values for AMD for optimized performance, which are these, and the other recommendations that AMD and the vLLM community recommended is these two flags that help with improving performance. And then we specify that we want to run it on 8 request. And then if you want to deploy this model, all you do is Helm upgrade install with the KubeAI models. We're using KubeAI to deploy this model on a Kubernetes cluster that has access to 8 of these MI300X GPUs. Okay, now that the model is up and running, we can start running a benchmark. Let's verify that the model is still up and running. Yes, we're getting health checks. And we're going to use the vLLM benchmark script, benchmark serving, which is part of the vLLM open source Git repo, which is this is the script that we will be using for benchmarking. And we run it by simply specifying that which dataset to use, and I have already downloaded the shared GPT dataset locally. I've done the port forward to my KubeAI API endpoint, and then we're specifying the model name, and you have to specify the tokenizer as well, since it calculates the tokens for the prompts that are being sent. And then let's run it. This is all we need to do to run a benchmark, and this is going to send 1,000 requests to the backend, and then it's gonna calculate the metrics for all these 1,000 requests. And this is a simplistic benchmark. It just sends all 1,000 requests all at once, and we should be able to see that. If we look at the year, we should see that's getting the completion requests all at once, as you can see here. I'm going up in history, and it got all 1,000 requests, and it should be starting to work on them. And as you can see, initially it's more prompt throughput based, and later we will see the throughput going up as this benchmark continues. And you can see it's now actively it's running 1,000 requests, and it's running all of them and it's sharing to the batch very quickly. We can also take a look at the other tab where we see that it's already completed 584 out of 1,000 requests, and here you can see the metrics as it is going through these requests. You can see that it's actually not like we could probably squeeze out more performance, because we see this GPU KV cache usage being relatively low. I think we could probably give it even more requests in parallel, and it would probably still be able to handle those pretty well. Especially towards the end, when it doesn't handle as much parallel requests, we see the aggregate generation throughput going down, since it is not running many requests in parallel anymore. And we are almost done, just waiting for the last few requests to finish. And that's it. We see it finished all 1,000 requests successfully. The whole benchmark took 138 seconds to complete all 1,000 requests successfully. And the average output or generation throughput was 1,200 tokens per second. And then the prompt and output generation throughput total was 2,900 per second. And here are other metrics. These are the standard results you will see if you run this simple Python script to do a vLLM benchmark. Hope that was useful. Thanks for watching, and let me know if you have any other configurations that you would like to see benchmarked.